Intuitively, two events A and B are thought to be independent if the occurrence of B in no way affects the probability of A occurring. This refers to the probability of the intersection of the two events. In fact, the probability of A intersect B is equal to the probability of A times the probability of B. In this picture, for example, we have a sample space S, whose probability is 1. We have an event B, shaded in blue, and an event A, shaded in yellow. The intersection between these two events, A intersect B, is shaded green. You can see from the nature of the picture that if probabilities were represented by areas, then the area of the green region is equal to the product of the area of A and the area of B. This assumes, of course, that the area or probability of the whole sample space is 1. Events are independent if the probability of an intersection is equal to the product of the probabilities. And if two events do not satisfy this property, then we call them dependent events. Independent events have the property that the ratio of that part of B which is included in A divided by the probability of the whole of B is exactly the same as the probability of A divided by the probability of the whole sample space, which is 1. If we have a large number of events, A1, A2 up to AN, then we call them independent if the probability of the intersection of any number of these events is exactly the same as the product of their individual probabilities. This has to be true whether on the left side or the right-hand side of this equation I have 2 events or 3 events or 4 events or any finite number of events. For every possible subset, I1, I2 up to Ik, this identity must hold. For independence among n events, it's not in general sufficient that they be independent in pairs or pairwise independent. In other words, if I pick any 2 of them, Ai and Aj, the probability of Ai intersect Aj is equal to the product of their probabilities. We'll show you an example of why this is insufficient for full independence in a few minutes. If we only have pairwise independence, 2 of these events may in effect gang up and provide information about, say, a third event, contradicting the usual notion of independence. Example. Let's suppose a box contains 7 red balls and 5 black balls, and we draw 2 balls from the box at random. A is the event that the first ball drawn is red, and B the event that the second ball drawn is red. If the balls are drawn at random with replacement, are the 2 events A and B independent events? What if we replace the with replacement draw by a draw without replacement? In other words, we don't replace the first ball after it's drawn before we draw the second. So the question is, are the events A and B independent of one another? Let's start by determining the probability of A. The probability of A is the total number of red balls in the box, that's 7, divided by the total number of balls in the box, that's 12, so 7/12. Similarly, the probability of the event B that the second ball drawn is red is again the number of red balls in the box divided by the total number, 7/12, since any one of the red balls could appear as the second ball drawn. Let's now determine the probability of A intersect B. This requires a red ball on the first draw and a red ball on the second draw. And since we replaced after the first draw, there are 7 choices for both, 7 times 7. Now how many ways can we draw balls for the first and second draw? In total, there are 12 balls available for both of these, so the denominator is 12 times 12. The probability of A intersect B is therefore 7 times 7 divided by 12 times 12. And this happens to be identical to the probability of A times the probability of B, showing that the events A and B are independent of one another. Now what difference does it make if we draw the balls without replacement? In this case, the probability of A intersect B is given by the number of ways we can draw a red ball in the first and second draw. There are now 7 choices on the first draw, but given that 1 red ball is already drawn, only 6 remain for the second draw. So the numerator is now 7 times 6. And similarly, for the denominator, we had 12 choices for a ball on this first draw, but only 11 remaining for the second. So the denominator becomes 12 times 11. And this is not identical to the probability of A times the probability of B, 7/12 times 7/12. Here is an example of 2 events which are dependent. This is intuitively obvious because your chances of drawing a red ball on the second draw are in this case lowered by the fact that you observed one on the first draw. These events are dependent. Example. This is a result which says, essentially, that if A tells you nothing about the probability of B, then that's true also of A complement, or not A. The mathematical statement is, if A and B are independent, so too are A complement and B. In order to show this, we need to begin by showing that B can be written as the union of two mutually exclusive sets. Here, for an example, is an event B, and we can write B as the union of the portion of B which is inside of A, that's this portion, and the portion of B which is outside of A, that's this portion. So this identity equates B with the union of A intersect B and A complement intersect B. And these two events are mutually exclusive. They have no points in common, which is to say they are disjoint. It follows that the probability of B can be written as the sum of the probability of these two mutually exclusive sets. Turning this around, the probability of A complement intersect B is the probability of B minus the probability of A intersect B. We are now ready to use independence, which attacks the last term in this expression, and writes it as the probability of A times the probability of B. Finally, if we factor the right-hand side of this equality, remove the common factor P of B, we're left with 1 minus P of A times P of B. And since 1 minus P of A is P of A complement, this becomes P of A complement times P of B. We started by assuming that A and B were independent, and we have now proved that A complement and B are independent. Of course, we could continue to prove that A and B complement are independent in exactly the same way, or that A complement and B complement are independent. Is it possible for events to be pairwise independent, independent in pairs, but not mutually independent? Here's an example. We toss two fair coins, a dime and a nickel. A is the event that the dime shows heads. B is the event that the nickel shows heads. And let C be the event that the two coins show the same, i.e., they're both heads or they're both tails. I want to begin by examining the independence of the events A and B. What's the probability of A intersect B? This is the probability of two heads in a row, a head on both of the two coins, which is 1/4. And that's exactly the same as the probability that the dime shows heads, 1/2, times the probability that the nickel shows heads, also 1/2. In other words, P of A times P of B. So A and B are independent of one another. Similarly, take a look at the probability of A intersect C. This is the probability that the dime shows heads, and the two coins show the same outcome. So, once again, the probability that they're both heads. And this is 1/4. And that's exactly the same as the probability of A times the probability of C. Similarly, the probability of B intersect C is 1/4, identical to the probability of B times the probability of C. But what about the independence of the three events A, B, and C? What's the probability of the intersection of the three events A intersect B intersect C? That means the dime shows heads, the nickel shows heads, and both coins show the same outcome. That's essentially redundant. In other words, it's the probability they're both heads, or 1/4. And that's clearly not the same as the product of the three probabilities P of A times P of B times P of C. That product being 1/2 times 1/2 times 1/2, or 1/8. So these three events are not mutually independent. They're dependent. That seems intuitively pretty clear. If you told me that both B and C occurred, in other words, that the nickel shows heads and the two coins show the same, you'd be telling me exactly what happened for the first coin, for the dime. Events which depend on independent experiments are independent events. That seems fairly clear. For example, I roll two fair dice, one red die and one yellow die. A is the event that the red die shows a 5. B is the event that the yellow die shows a 3. Can you show that A and B are independent events? Let's start by determining the probability of the intersection A intersect B. That's the probability of the pair, 5 on the red die, 3 on the yellow die. 1 point in a sample space consisting of 36 points, 36 possible pairs. So 1 over 36. On the other hand, the probability of A, it's 1 out of 6 possible values for the red die. The probability of B, similarly, 1 out of the 6 possible outcomes. So both A and B have probabilities 1/6. So the probability of the intersection, 1 over 36, is equal to the product P of A times P of B. In this case, the two events, A and B, are independent. That's intuitively clear because one depends on the red die and the other entirely on the yellow die. Independence is, however, not always completely obvious, as the above independent events were. Here's an example. Again, I throw two fair dice, one red and one yellow. A is the event that the total on the two dice is 7. B is the event that the red die shows fewer dots than the yellow die. And the first question is, are A and B independent events? Let's determine the probability of A. It, of course, are pairs of numbers which add up to 7. So 1, 6, 2, 5, 3, 4, up to 6, 1. Since there are 6 points in A, out of 36 possible pairs, probability of A is 6 over 36, or 1/6. What about B, the event that the red die shows fewer dots than the yellow die? The event B consists of pairs like 1, 2, 1, 3, and so on, any pair of numbers such that the first number is smaller than the second. It's a pretty simple counting argument to determine that the number of such pairs is 15 over 36. There are 5 starting with 1 and 4 starting with 2 and so on, for a total of 15 over 36. What about the probability of A intersect B? A intersect B says that the total on the two dice is 7 and the red die shows fewer dots than the yellow die. The event A intersect B can happen in 3 ways. The total has to be 7, and the first number has to be smaller than the second. So we have the pairs 1, 6, 2, 5, and 3, 4. And those 3 points have probability 3 out of 36, which in this case is not the same as the probability of A times the probability of B. So in this case, the events A and B are dependent. Let's look at the possible independence of the two events A and C. We begin by calculating the probability of the event C, that the yellow die shows a 5. This, of course, is routine. It's 1 over 6. The probability of A intersect C is the probability of the 1.2, 5, the only outcome that satisfies both conditions. The total is 7, and yellow die shows a 5. And of course, that's 1 out of the 36 possibilities. It has probability 1 over 36, which in this case is exactly equal to P of A times P of C. So A and C are, in this case, independent of one another.